Here we go, applications of determinants. One of the main applications is something called Kramer's rule. Now, I want to make sure everybody's got a calculator handy and ready to go because it's going to take too long on some of these 3x3 and 4x4 to do the determinants like that. Okay. So, so what I'll probably do too is try each person to group here. Here's Kramer's rule. It's used to solve systems of linear equations. That is, where all the powers of the variables are 1, and they're separated by terms. 3x plus 5 equals 7, 4x plus 9 equals 11. And here's the formal definition of these things, d sub x, and d sub y. I think it's easier just to watch what I do on this to see what I mean by d. D is the coefficient, it's the determinant of all the coefficients on the variables. So you see where I got 3, 5, 4, 9? I just took the coefficients on x and y. Now you do have to get into a standard form for Kramer's rule. You've got to make sure your variable terms are on the left and your constant terms are on the right of the equation. You've got to make sure you arrange them in a set order. And so this determinant is 27 minus 20, or 7. That's d sub x. Now, we actually make a copy of d again for both of these. Now, if you're using pen, this doesn't work out so well. If you're using pencil, it works out great. But with d sub x, you replace this x column, you erase it, and with d sub y, you're going to erase the y column. This is a standard technique no matter what size your system of equations is, 2x2, 3x3, or 4x4. And now we replace that column we just took out with what else is there? 7 and 11, right? The constant column. The constant column sneaks into the x column. That's how you get d sub x. And for d sub y, we took out the 5, 9 coefficients on y and replaced them with the constant column 7. Okay? Did everybody see that? I'm going to highlight that difference because it's so K. There. 7, 11. All right? Now let's actually calculate those out. Then you get 63 minus 55. That works out to be 8. And here we get 33 minus 28, and that works out to be 5? 5. Okay? So, all you have to do now to find x is take the ratio of the determinants. D sub x is 8, and d is 7, so x is 8 sevenths, d sub y is 5, d is 7, so y is 5 sevenths. So that's your point, 8 sevenths, 5 sevenths. Boy, I wish I had put the answer down. We better check this somehow. You can solve it the old ways. Let's do the TI-89 check on this. Do you know the TI-89 check? I'm not going to accept this as work. Right, it's called simul equation. It's in your apps menu. If it's not, I can download it in there, at some future date. Simultaneous equations. It's very handy, okay? Did you find it? Simultaneous equations. And you have to tell the size right away. How many equations do you have? 2. And then it enters the coefficients straight because it goes like A1, 1, B1. No, I think it's A1, A2, and then B1 for the constant. So, in either case, I think it usually lets you enter into a matrix, right? Or it's got, does it have a, yeah, it shows you a little grid. And as you enter, it'll go to the right, like a tab, and come around. So what were the coefficients again? It was 3, 5, 7. 4, 9, 11. Okay? And then it'll usually give an answer in x1 and x2. It doesn't say x and y. This way you can go up to, I don't know, like 40 equations and 40 unknowns. So you don't run out of letters in the alphabet. Okay. And what does it say? Right. Yeah, it's not going to give you the exact, and that seems to be consistent. 1.142887, 1.142857, and that's a repetant, and that's 8/7. And the other one, 0.714285. So you notice how your sevenths repeat 6 digits. It's one of the cool things about 7. Okay? Are you set with that process? Now, you might say, is that any easier than linear combination? You know, what would you do with linear combination on this? If you add them up right now, you get 7x plus 14y equals 18. That doesn't work. So you prep them first. You can use substitution too, but linear combination, like multiply the top one by 4 and the bottom one by -3, add them up, and then the x's will fall out. And then you can kind of see how we're coming up with that AD minus BC, that ratio of the determinants that we to figure out what the coefficients are. See, I'm talking about substitution, solving this for y. 5y equals 7 minus 3x, y equals 7 minus 3x over 5, and then sub it into the other equation. That can get us into fractions, right? Yeah. It's a little like what we did with synthetic division. You all love synthetic division so much, right? Oh, yeah. But now you had to have it in a very special form, right? It was only for sigmoid division. You had to be able to write it as x minus something and divide it into a polynomial. And the whole point is you got rid of all the repetitious sayings of the x and y's and used the columns to represent things. So that's what's going on with this. Notice, there's no x and y here except for these indicated subscripts. You're just working with the numbers in a process to come up with the answer. Now this works for any number. So let's hustle through this. Hey, as long as you got this out, do you want to check our answer right now? Because I don't think I wrote it down. I did. It's 153. You can check that at your leisure and see that you can do this on Simon as well. But if I ask you this on a test, I want you to set up Kramer's rule to solve this. So we need to come up with our different things here. And we've got 4 groups and 4 determinants to figure out. You all got D sub x, D sub y, D sub z. Go. This is a race.
Go, Z!
Empty pips to the loser. Well, they all come in tips. Careful on this z here, that's a -1. Don't make it a 0. Right? Now these determinants let you do on your calculator. Don't try to do them by hand. What? Yes. And I'll keep making the d sub x's here. D sub y. D sub z. Oh my gosh, we have a winner! What do you got for D? -30, okay. I don't know if that's right yet or not. Okay, yeah, double check. Double check.
Actually, I put in the exact same thing.
-90 for our thing.
Really, is that how your group functions? One person's on the calculator?
Or just
What do you do there? DPW.
That's what I was wondering. Put the emphasis on the G, so it's like actually Jesus.
Okay, and then maybe green will show up nicely here. Our constant column, 4, 14, -4. 4, 14, -4. 4, 14, -4. And what do you get for these determinants here? Oh, we got a group for D sub z here, yes? -90. Now that's usually a good sign because if they're going for nice answers, you can see this ratio is working out nice, right? Okay, so always the middle child.
I'm trying. Don't worry.
Just use the ratio.
Now it's a syntax. Wait, -1
150?
Yeah.
Okay.
It's negative 106. Wait,
Negative-
no.
It's negative 30.
You got 10 seconds to avoid the answer.
Wait, what? You said it wasn't real. Wait,
You're
now
not
it's
right.
negative 30. And
You don't need
negative 30.
adjectives for this behavior.
How are you counting this?
It's negative 30.
Are you going one way to six?
And you all have most people to work on it. I
Oh,
guess the calculated person ratio is too low. Negative
30.
30. Okay. So now we're ready to go to the next step, and this is where these D people better be right. Right? Because x then is d sub x over d, negative 30 over negative 30, you get 1. Y is d sub y over d, negative 150 over negative 30, you get 5. Z is d sub z over d, negative 90 over negative 30, and you get 3. Bing! Checks out.
Yeah, use Google.
Watch this miracle of technology. Oh, yeah, there's the answer. Okay. All right. So that's Kramer's rule. If I have you do Kramer's rule, if it's a 2 by 2, I'd expect you to do it by hand. I think it would be faster than entering your calculator. But for 3 by 3 and up, you can go ahead and use your calculators to figure out those determinants. Don't sit there and stress out over all that. Now, we can also come up with areas of parallelograms from a vector's 2 adjacent sides. We can come up with its area. And it's pretty amazing. It goes like this. If I have one vector, and we'll call this AB, and another vector CD, forming determining a parallelogram, right? Because I can actually apply this vector over here then. Come up with a point up here, right? I can take CD and add on AB, and I'll come up with A plus C, B plus D over there. We get its area by just doing the determinant, the absolute value of this determinant. The absolute value of the determinant A, B, C, D. It's that amazing. Okay? Wow. Yeah. You can work out a proof on this at home. Okay? That would be worth multiple image. Yeah. And it's also kind of, notice if you use lattice points on a grid and you make a parallelogram, and you look at all the little squares and so forth and all those little partial triangles, that's another PIP project. Cut that out, show out all those little squares and little triangles actually form together to make that exact whole number. Because if I start with all whole numbers here, this is going to be a whole number, isn't it? The determinant. And so you get a whole number area. Now notice we did see some determinants go negative. That's why you need the absolute value. So this is not some sort of funky double vertical line. It's two separate things. This outer one, this is the absolute value. And the intercept is the determinant. So it's the absolute value of the determinant of the matrix. Okay? So you actually have to, if you're going to do it in your calculator, you do DET, and then you might get a negative answer, just know to make that positive. Okay, what?
This is kind of off, well, it's off topic, but you know how when we were freshmen, you let us get pips if we ran around in the snow?
Oh, yeah.
Oh, then to make that ellipse, yes, okay.
I remember Joe did that.
For an ellipse,
Yeah.
why not a big snow diagram demonstrating this geometric application?
Yeah, you did.
Oh,
You make a big grid pattern in the snow, and then someone does a vector, and you make the parallelogram, and you can take a picture of that.
you did.
Yes, there you go. I wouldn't do it today. There you go. There you go, Spot. Further, oh my gosh, we can do it this way. We can say, okay, we got vector ABC. This is called a parallel pipette. It's a 3D figure where all the edges, well, 4 of the edges are parallel, the other 4 edges are parallel, and then, yeah, those front to back edges are parallel. It's 6 parallelograms put together, right? So it's called a parallel pipette. You know, if you made this a 90-degree angle for all these, then you'd think of it as a box. Yeah. So it's all one parallel pipette. And you take the vectors of the 3 edges coming out of a common corner. So let's call this ABC, and that shows up here as ABC. And again, I'm doing the double thing there because you could possibly get a negative determinant, so you have to take the absolute value of it. ABC, and here's DEF. GHI. GHI. And again, this outer one is actually the absolute value. And then this inner set is the determinant.
Is one of those one of them is bigger than the other, or
Question here, please.
to differentiate, like if you're writing it out, is one of them bigger than the other, or they the same size?
Yeah, they're the same size. Yeah, that's a good question. Because remember when I first said the determinant is kind of like an absolute value, that's why I use the vertical bars again, because it's returning a number for a whole bunch of numbers, just one number. But unlike the absolute value, it can give a positive negative answer, so. It's kind of like the absolute value for matrices. All right. Find the area of a triangle with vertices at 1, 2, 3, 6, and 6, 1. And this is what I was talking about for those of you who want to do that snow project. If you were to just sit there and count squares, so you connect these two, but notice they don't really connect up quite right, do they? And we're going to get the area of the triangle. The area of the triangle will equal half the area of the parallelogram. And remember, the determinant tells you the area of the parallelogram. And so you could try and count these squares and then look at how some of these, like this little partial triangle would come over here to finish that up and you get a whole square there. So you could try and count the area right now. Should we?
Yeah.
We got definitely a whole one there. 1, 2, 3, 4, 5, 6. It's tricky. Oops. I think this one comes over here for 7, and that little notch it here comes over here for 8, and then 9, and then 9, and then, sorry. Yeah, I think 10, and then there's like maybe 10 and a half, or 11, or make 11 when these two come together, right?
Let's see.
Yeah, let's see. So, we do this though, we've got to come up with the vectors first. PQ, the vector PQ, is 2, 4, right? Don't just put the corners in. You've got to get a vector coming from a common corner. So this is the vector 2, 4, and PR is the vector 5, negative 1, okay? And that's how we're going to do our parallelogram, PQ and PR. Now, it doesn't matter which one you put on top, because if it ends up being negative, you're going to do the absolute value anyway. So you got 2, 4, 5, negative 1. So that's negative 2 minus 20, negative 22. The absolute value then of negative 22 equals 22. Is it 22? I thought we had 11. It's half, right? And so the area of the triangle equals half the area of the parallelogram. So 1/2 22 equals 11. Check. And then check down with a little column too. Yeah. But, my dots on here are so large and my lines are a little off. If you do it really precisely on some decent graphing or in the snow, make sure you have an overhead cam.
And
Okay. So that's area of the parallelogram. All that leaves then is, there's the area equal 11. Yeah. Oh, and that's it. Okay. So, we got some time. We got 20 minutes to work on stuff. Tiva initiated a nice initiative the other day that, I could also leave this up if Kimberly and Tiva just want to work on their problems up here. It's up to you. Okay. And I can back up. You're all set with that? Okay, so let me just stop this one then.
Go ahead.
Stop.